Hello, my name is Anderson Silva. I am a PhD candidate at the National Laboratory for Scientific Computing in Brazil. Today, I'm going to present my work called Towards an Integrated Solution for IoT Data Management. In the last 2 decades, the number of IoT applications has been growing in an extraordinary rate. Some examples of different applications are in object tracking, anomaly detection, real-time analysis, and decision-making. These applications are used in the most diverse domains such as smart homes, smart cities, smart healthcare, industry, sports, and so on. However, processing and analyzing continuous data streams from heterogeneous networks creates a number of different challenges, and these challenges demand the development of new technologies and services. So, what are these challenges? First, we have challenges related to large-scale IoT data management. IoT data is usually constituted of a big range of heterogeneous endpoints that both produce and consume a massive amount of unstructured data. There's usually no standard structure among different devices. These devices are usually geographically distributed, which makes space and time correlations particularly relevant. This is a problem for more traditional systems such as database systems, since they cannot fulfill the requirements that these IoT data streams demand. Quick response is by far one of the most crucial demands. Because data is generated at high volumes and high speed, it's not acceptable to perform heavy operations such as disk writing before the processing of the messages. Also, these characteristics create a scalability and security requirement since new data sources may be added or removed from the environment in real time. Last, there is also a resource constraint issue that must be taken into account in terms of memory usage, bandwidth, and energy consumption. Another set of challenges is related to real-time analysis. Not only IoT environments produce data on a large scale, but also this data needs to be analyzed in real time. Traditional environments may process data in an offline form, which means receiving all data before processing. However, IoT data is continuous and potentially never ends. Therefore, this demands the use of lightweight data mining algorithms. Another issue is characterized by the lack of integration between the data processing system and machine learning. Machine learning strategies are very commonly used to perform analysis on IoT data. However, when dealing with a database system, for example, the lack of integration between the database and the machine learning tool makes some optimization tasks such as query planning and lazy evaluation impossible, because the two tasks are treated as completely isolated processes. Finally, IoT data is specifically subject to the problem known as concept drift. This is a problem related to prediction models that happens when the statistical properties of a target variable change over time. When that happens, the performance of the model tends to drop, and this leads to poor predictions. Therefore, an ideal solution should be able to detect and react to a concept drift. We consider as our use case example an extreme events monitoring platform. In such an environment, we have a very heterogeneous set of data sources, such as cameras, pluviometrical radars, and many different types of sensors. These devices produce continuous data streams. These data streams generate a lot of data that needs to be analyzed. But not only are there many source devices, but also there are different types of users that may have different interests in accessing the system. A specialist, for example, may be interested in accessing the platform to check and validate potential alerts generated, thus being both a consumer and producer of data. But a data scientist may access the platform in order to perform some kind of historical analysis on the data and identify potentially relevant patterns or train prediction models. Also, some parts of this data may be made available to general public. Therefore, this big range of users also create a security issue since not all parts of the data should be necessarily available to all users. We believe that there are three different approaches for database systems that can provide interesting features for handling IoT data. The first one is actor-oriented databases. Actor databases are able to handle scalability issues using actors, as well as privacy and security through encapsulation. Active databases philosophy provide reactivity in event processing, and array databases provide access to operations from array algebra and also a flexible storage format for handling sparse arrays, for example. However, to the best of our knowledge, no solution has been proposed to integrate all three different approaches. Actor-oriented programming is a programming paradigm that simplifies distributed system developments by using actors as its fundamental programming unit. Conceptually speaking, actors exchange messages using a queue mailbox. They don't share memory state, they process one message at a time and have no multi-threaded execution inside their state. There are many different actor-based frameworks, languages, and toolkits that have been developed. Some famous examples include Erlang, Eka, the Wave Framework, and the Elixir language. Actor-oriented databases were proposed in order to also benefit from actor advantages. There are two complementary approaches for building actor-oriented databases. The first one is to apply database functionalities into an actor framework. This is the approach taken by Microsoft Orleans, for example. The other approach is to insert actor primitives and ideas inside a database model. This approach was the one introduced by PhDWorkshop, a database system developed at the University of Copenhagen. What is interesting is that because of actors' adequacy for distributed systems, scalability, and data encapsulation, they provide interesting primitives for handling an Internet of Things scenario and addressing these characteristics that I mentioned before. Another potentially interesting strategy for handling IoT data is the use of array databases. Array databases were developed in order to provide data management and analysis based on array algebra. Because of that, they are especially adequate for multidimensional data applications. They provide an implicit star ordination, which means that data access over dimensions can be easily and quickly performed without the creation and storing of indexes, which also means that they need a smaller storage space. Even more interesting, they also enable data analysis based on array algebra operations such as array slicing or subsetting using declarative array query languages. Many array frameworks and databases have been developed on the last decades, but probably the two most famous databases are CiteV, developed for scientific usage, and Hasdemon. Finally, a third interesting approach for databases that could be useful in an IoT scenario is the philosophy of active databases. Active databases were proposed some decades ago in order to turn databases reactive systems in opposed to passive software that only responds to queries. They were based on ECA rules that specified events, conditions, and actions. The principle was that predefined events determine when rules should be activated. The conditions of an ECA rule determines whether the action should be executed. And finally, the action of an ECA rule determines how to react if the condition is evaluated true. Complex Event Processing Techniques, or CEP, extended the logic behind ECA rules by introducing real-time stream processing for monitoring and detection of arbitrarily complex patterns in massive data streams. In CEP, each data item is abstracted as an event produced by a data source. Multiple simpler events can be combined to produce more complex ones that match predefined patterns. Because of its efficiency for handling continuous data streams, CEP are an interesting approach to be employed on IoT environments. Now about the concept drift problem. The phenomenon known as concept drift is a situation that may occur when using machine learning-based analysis, in which the statistical properties of a target variable change over time in an arbitrary way. The reasons for that are usually because there were changes in hidden, not measured variables. When that happens, the model's accuracy tends to drop. The situation should be taken into account when building an efficient IoT data platform. So in a typical scenario, there might exist a classification problem in which it is necessary to analyze examples of two different classes with a boundary that separates them. Over time, changes on the environment may cause this boundary to be altered, making that some sets of features be classified as different classes. This is known as a real drift. There can be also a shift on the data distribution without changing the classification of examples. In this case, some authors call this kind of drift as virtual drift. There are many other classifications of concept drift according to their source, their behavior, and their locality, and also different algorithms for handling each type of drift. that should be included in an efficient data management and analysis solution. Therefore, these are our research goals in this work. We aim to develop a new data management solution suitable to IoT environment requirements. We intend to combine the main approaches of active, actor-oriented, and array databases, and we aim to provide a scalable, reactive, and efficient data management and analysis system for IoT. We also aim to integrate ML inference into the data management system, enabling optimizations that would not be possible when treating machine learning analytics as independent processes. Finally, we aim to integrate an adaptive concept drift detection method into our solution that considers the characteristics of IoT data. This table illustrates our vision for this solution. With actors-based programming from actor-oriented databases, we intend to provide dynamic scalability, asynchronous primitives, and encapsulation for IoT environments. With array-based data management, we provide array-based operations that can be very interesting for distributed devices and a flexible storage format. And with complex event handling, we provide event detection and reactive behavior. As another interesting feature, we intend our solution to support machine learning model execution by providing machine learning as first-class operations and also concept drift handling. This is the design of our prototype solution. In this scenario, we have a three-layered system to address an IoT environment. The first layer is responsible for the data collection from sensor devices, while the second layer is where we perform local operations in parallel. There is also a working storage that is the data entry point, a query processor that is able to execute continuous queries and format the data structures in order to send them to the global processor on the third layer. There are also a concept drift detector and an event detector that analyzes continuously the data, searching for relevant patterns or anomalies. Finally, in the third layer, we have the central global analyzer that is prepared to perform heavyweight operations such as historical analysis and global pattern detections. We employ an array data manager on this stage in order to execute array-based operations and array algebra. As future directions, we intend to evaluate the solution on a weather prediction and monitoring scenario, as specified in the beginning of this presentation. We also intend to compare the solution to an approach that integrates different already existing data systems. Finally, we will measure scalability and performance of the solution when compared to state-of-the-art techniques and systems. This is the end of my presentation. I thank you for your interest, and I am open to questions.